Here's some guidelines on capture velocity for sedimentation tanks. And we'll connect with how you actually design a tube settler or a plate settler in just a little bit. So Brentwood Industries out of close to my hometown, Reading, Pennsylvania, makes tube settlers, and they recommend between 0.12 and 0.36 millimeters per second as the capture velocity. That means you take Q divided by the plan view area of that system, and that's what that capture velocity is. For horizontal flow tanks, capture velocities between 0.24 and 0.72 millimeters per second. Agua Clara, we looked at those numbers, and because in the beginning we didn't use filters, we were very interested in being conservative on our flocculation and our sedimentation side. And so we adopted 0.12. So we took it right off of Brentwood Industries, off of their website, and used that. And then just a reminder that now we have some messy equations that are actually pretty easy to use. If we know what zeta is, that give us a connection between the required capture velocity or the maximum capture velocity and what the velocity gradient is inside our flocculator. In any case, we ended up using 0.12 millimeters per second for our design. And we're all about making sure that we have a plate settler that has a capture velocity that's small enough so that it reliably captures the flocks that we need to remove. Is it clear to you? Oh, is it clear that a good sedimentation tank has a small capture velocity? Capture velocity is always confusing. Capture velocity is a property of the tank or of the plate settlers, and it says how fast does a particle need to settle in order to be reliably removed. So if you have a capture velocity of 1 millimeter per second, that means that a particle has to settle at least 1 millimeter per second to be removed. If you have a capture velocity of 0.1 millimeters per second, now you can have a particle that's settling very, very slowly and you will still capture it. Okay, so a low number for capture velocity is good. Usually big is good, here small is good. It makes sense? Okay, so let's do it. We're going to look at plate settlers. So now this is very different geometry. Now we have plates at an angle, and we've got particles flowing up between we got water flowing up between those plates, and there's our critical path that we've got to have particles follow, and we have to figure out what does this notion of capture velocity mean on a plate settler. So there's a couple different things that have to happen here. The flocks have to be able to settle and land on the plates before the water exits. So that's about the capture velocity. And it must not slide or roll up the incline. I'll use this as a constraint to tell us how close together we can put plate settlers before we run into trouble. And it has to roll down the plates and combine with other flocks and land back in the flock filter and become a contributing member of society or a contributing member of the flock filter. So here's the critical path for capture. You saw it on 2 slides back. There it is. That's what a particle is going to do that we just barely capture. Or really in a plate settler, maybe it looks more like, oh, I guess I didn't do that. Okay, so that's the path that particle actually takes. So that's the critical path. And our goal now is to turn that into a capture velocity. So let's try it again. Here it is. What's that path? It's this is the path. It has to take that slight angle and slowly get to what it sees as the lower plate, right? It's in between 2 plates and it always ends up in the lower plate. During the time that the particle took that path, what did the water do? You know, the water, okay, I have a couple of vectors at the bottom here. There's VZ plate, that's the vertical component of velocity between these plates. And then there's the angled component of velocity, which is, oh, this is one of the things that I think students find confusing, and I find confusing too. When water enters plate settlers, we're going to take a vote just for fun, okay? So gird yourself. We're going to take a vote. When water is going up through the flock filter and then is going to enter the plate settlers, when water enters the plate settlers, does it keep going the same velocity? Does it speed up or does it slow down? So think about this for a second. Water's going up and then there's these plate settlers above it. And to make your life easier, you can pretend that the plate settlers are infinitely thin, just to avoid that confusion. Okay, so you got these infinitely thin plates, and I want to know, does the water speed up or slow down when it enters those plates? Oh, look at Pat. Pat is super.
Votes are coming in. It's a close race, so a couple more and then we'll close the poll.
Wow, look at this. Isn't this great, guys? You know, what's fascinating is, I think you realize that there's actually one answer that's right. And yet you're all over the place. And it's because this idea is confusing. So how do we think about this? Can you think of any relationships that are at least like friendly for us for helping to figure this out? Anybody think of some physics that might help us here? Some relationship that must be true? We call that continuity or mass conservation. Somehow the water that's going up into these plate settlers has to leave them at the rate that it's coming in. Oh, well, look at that. That does it very nicely. Compare the width between the two bottom points of the plate settlers. Compare that width with the perpendicular width, S. Which one's greater, S or S over sine alpha? The opening at the bottom. Ooh, so this, do you see this? S over sine alpha, this opening at the bottom of the plates is actually bigger than S. And at the bottom is where the water is entering vertically, and then it takes a turn, and in order for that same flow rate, because the area is less as it's going up at the angle, the velocity had to increase. Oof. So is this craziness? We have to decide whether or not we want to buy physics. So it does, the water actually speeds up, and you know, that was actually hiding there in my two little vectors at the bottom the whole time. There's VZ plate, that's the vertical component of velocity. V alpha plate is in the direction of the plates, and it's a little bit bigger because now the velocity, the water has both a vertical velocity and a horizontal velocity that gets you the V alpha. Okay, so it actually speeds up. Okay, And I needed to know the water that was carrying this particle up through the plates. How far did that water travel in the time that it took for the particle to go along its critical path? And I'm going to put this in here because it's just, maybe it's also a surprise. Look, it had to, hang on. It landed way up there at the top of that arrow. Now you're thinking I'm really bonkers, right? The water that was traveling straight ended up at the top of that arrow. And during the time that the water was traveling up between the plates, the particle was settling down at its terminal velocity. And it was doing that the whole time. And so let's see what happened. That arrow is the distance that the particle traveled down while it was being carried up by the flow. Right? It entered right next to the top plate. It exited on the bottom plate. So it traveled the red line vertical distance. But it ended up at the top of the plate. So what happened is the water traveled from this bottom entry point all the way to the top of the red arrow. While that was happening, the particle traveled a distance of the red arrow down, and that got it to follow the blue path. Okay, so the blue path is the combination of what the water did and then what the particle did relative to the water. So we can figure out what HC is. It's that vertical distance between the plates, S over cosine alpha. What's the total vertical distance that particle will travel? It actually travels distance h, right? During the time that the particle is traveling between these plates, it actually travels distance h, and that's equal to L sine alpha. And its net vertical velocity is the addition of how fast the water is traveling vertically minus how fast gravity is pulling it down. So you got water carrying it up, gravity pulling it down, and VZ net is the net velocity of that particle in the vertical direction. So it's traveling a distance h at its net vertical velocity, and it's traveling a distance hc at its terminal velocity. And that's going to be our little trick that we're going to use to solve this. And oof, I feel like equations are always a pain. I'm hoping that you followed a little bit about how those vectors work. We're going to take the two times, the time to travel distance hc and the time to travel distance h. Those times are the same because it's just, that's how long it took for this particle to get to where it landed on the lower plate. And it travels a distance hc at its capture velocity. That's how far it had to settle to get between the two plates. It travels a different distance h at its net vertical velocity. And then we can do a bunch of substitutions. And I think at this point, I'm just going to fly through these because you don't want to see it, okay? I'm just going to go to the last equation, which is a lovely relationship between the vertical velocity entering the plate settlers and the capture velocity of those plate settlers. And it's the addition of 1 plus L over S times cosine alpha sine alpha. And what does that mean? Well, VZ plate is a big number, like a millimeter per second. I know that's not very big. VC is a tiny number, like 0.1 millimeters per second. So VZ plate over VC is a number something like 10. And cosine alpha and sine alpha, when you multiply them together, I forget what it ends up being. I think it's something like half, roughly, which means that L over S has to be a big number, like 20, in order to make this work. So that's indeed how plate settlers work. They're long and they have a short distance between them. And that L over S is what determines like how efficient they are. So we did all of this because we didn't want to build a huge horizontal sedimentation tank, because a big horizontal sedimentation tank is expensive. And this is going to save us a ton of money because we can reduce the overall size of the tank by the factor. So if VZ plate over VC is a factor of 10, then we can reduce the size of the sedimentation tank by a factor of 10. And if you had a factor of 10 increase in your salary, you would get excited, right? So a factor of 10 is a cool thing. And it means we're saving that much money on these sedimentation tanks, except we're going to invest more in plate settlers, but plate settlers are cheap compared with all the concrete. So here's our design. We use a millimeter per second up through the flock filter. That determines the plan view area of the sedimentation tank. We use 0.12 millimeters per second as our capture velocity in our plate settlers. That determines how much plate settler area we need. But then are you wondering, like, where did this 60 degrees come from? Like Monroe just pulled that out of the air. Just like, oh, 60 degrees. Where did that come from? Any ideas? And while you're thinking about that, remember Monroe's rule? Go to extremes. You've already gone to one extreme today and thought about failure. So go to both extremes and think about failure, and then think about like what's good about being in the middle. Okay, that is your question. Okay, you're trying to understand why is it good to have plate settlers that have some angle, which Monroe randomly pulled out 60 degrees. Not all plate settlers are at 60, some are at slightly shallower angles. I don't think there's anybody that goes steeper. And the question is, what fails if you go to 90 degrees or if you go to 0 degrees, and what is good about being in the middle? That's your question?